We are going to make a very brief derivation of the Black-Scholes equation that we're going to solve it numerically later. So first we can write the option value as a function of two independent variables, which are going to be the asset price and time. And besides that, we also have some other parameters that will arise in the different models that we'll be using. So this sigma will be the annual volatility of the asset. This mu is the average rate of growth of the asset. This E will be the strike price. Then we have the maturity time associated to the option, the interest rate that we do have that we'll consider to be constant, as well as the volatility will be constant. But all of these, they are like parameters. So in principle, the two independent variables we do have here is just a two-dimensional model. In this two-dimensional model, we just have one asset here. It's the asset price and time. So the next step is that we're going to build a portfolio, where this portfolio we're going to call it a pie. And this portfolio will have one long position of the option on one hand, and on the other hand we have a short position of some delta quantities of the underlying asset. So this delta will be considered to be a constant here, and therefore the value of this pie portfolio will be the following. This is the option, which is a long position, that's why it has a positive. Then it's a short position of delta quantities, that's why we have here a negative value of some delta, which is a number, times the value of the asset. And we are going to consider that this asset here follows a stochastic process, and we can model that stochasticity, considering that this asset is following a log normal random walk. And this basically is the following. We can write the variation of the asset price in a dt time interval in the following way. It has like a non-stochastic contribution here. This is the one. And we can write in the non-stochastic one in this way. This is mu. It's the what we define as the average rate of growth of the asset price, then times the asset price times the time interval we're considering, which is dt. So as you can see here, the change is going to be proportional on the asset price. This is why it's log normal. This is a log normal process. And of course, it's going to be proportional to the time interval, which is dt. And on the other hand, we have the stochastic contribution here. We have different parameters. The sigma is the annual volatility. Again, this contribution, so the change is going to be proportional to the asset price. And this is the stochastic contribution is given by this dx. And dx, for that dx, we are going to consider it being a process. And a linear process defined the following way. So dx basically is the change on the x variable, which is a stochastic variable, on a time interval dt, can be described by a normal distribution of zero average and standard deviation 1 times the square of del t. We're writing this square root, we're multiplying that by a square root of dt, because the average or the stochastic process of this log normal contribution it will have and standard deviation of this process in the time interval dt. So the stochastic and the standard deviation of the time interval dt will be the annual one, which is the sigma, which is the volatility, times the square of the time interval. So that's why we're considering, we are putting this square root of dt in the stochastic process of the x variable. Okay, so it's important to take into account that we're making the square of the x basically and making the average. So the average of this one, and we're taking the average, we're making the average of the one, and making the average of the square of this one will be 1. And the square of this one is dt. So the average of the square of dx of this stochastic process is proportional to dt. So and that's going to be important. Why? Because when making the square of dx here, we're making it here, here. So making the square of the s, we'll have different contributions. So we'll have one contribution will be mu squared, s squared, dt squared. Another contribution will be the square of sigma s squared, ds squared. Another contribution will be the product. So 2 times, so I'm writing it here, plus 2 times mu s dt sigma s dx. So here I'm taking the average of all of this. You can see that we have making the square of ds, we have a contribution which is non-stochastic contribution, which goes that the square of dt. But we'll have another contribution here that the square of dx, and taking the average of this one, is basically dt. So this one is basically dt. So you'll have that the square of ds will have a contribution which is proportional to dt. And another contribution here, this is proportional to dt times the average of this ds, which basically is 0. So here will not contribute. But the thing is that the square of ds will have a contribution which is linear on dt. And that's going to be important because on the following, we'll analyze with the change on this portfolio, and we'll just keep the linear contributions. But even though we'll keep the linear contributions, we'll need to go up to second order on the s here, because just going that, when doing that, and because of the stochastic process that the s is following, we'll have a linear contribution on dt. But we'll insist on that in the following and later. So first, basically, we have just defined this portfolio and just consider that this asset is following a log normal random walk. And the following we'll analyze what's the change on the value of the portfolio when we make a change on ds and dt. And we'll keep and consider just linear contributions on ds and dt. And that's what we're going to do next. So here we'll consider a change on the value of the portfolio in the time interval dt. So just having in mind that the value of the portfolio is just the value of the option minus delta, which is constant, times s. So we're making the derivative of this, or the differentiation of this portfolio. We'll have a differentiation of b minus delta times the ds. So as the v is a function of s and t, we'll write this differentiation on the value of the option in terms of ds and dt. And we are going to do that, and we are going to write that even though we are going to keep just linear contributions on ds and dt, I'm writing here up to second order, using the Taylor expansion, the change on dv due to the change on s and t. But we are doing that going up to second order on these changes. Why we are doing that? Because in principle we should just cut it here when you just want to keep linear changes on ds and dt. But here this s variable is not just a normal variable, it's a stochastic process. And in a stochastic process we do have, as we have said before, that when we are considering the square of the s, we have a contribution which goes like is linear on dt, the square of sigma s squared and dt. So that's why here, even though we have the square of ds, this is basically this one. So as you can see here, we need to go up to second order on ds in order to keep this linear contribution on dt due to the stochasticity of the s variable. And this is what's called the ethos lemma. Then these other contributions here that goes to the square on dt, we can neglect that because it's higher order on dt, and this is also, you can neglect that because it's also higher order on dt. So we'll just keep this contribution here on the square on the s, and from here we'll just keep the linear term on dt and eliminate these higher order terms. Because of course when making the square on ds, we also have another contribution here which goes like the square on dt, but this will eliminate when we just keep the linear terms. So when doing that substitution, we are substituting ds squared with this one. We do have the change in the value of the option can be written in this way. So this is what we already have it here. And when substituted by dv by the whole expression, this is we can write therefore the value, the change of the value of the portfolio in this way. Now, this delta here, which is a constant, in principle we can choose anything we want, and what we are going to do, we are going to choose a particular value here. We are going to choose delta to be the partial derivative of v with respect to s. That's what we are going to choose. Because when doing that, then what happens that this will go to 0. So choosing that particular value for delta, we have this contribution which is proportional to ds disappears. And therefore, what does it mean? That it means that if we choose that particular value for delta, we have that the randomness associated to this stochasticity of this s variable. So therefore, the risk when taking that portfolio is reduced to 0. This is what's called the delta hedging. Taking that particular value for delta is what's called the delta hedging, which is actually related to the value of the option. Then, for that particular value of delta, we have that the risk disappears, this disappears, then we just have that the change of the portfolio can be written in this way, and we have, therefore, that the change is completely riskless. Then it means that it must be the same as the growth we will get if we put the equivalent amount of cash in a risk-free interest-bearing account. Then it means that the change on this portfolio could be written in the following way: the interest rate times the value of the portfolio times the time interval we are considering dt. So these two, in case there is no arbitrage, then in case of no arbitrage, this is the one of assumption we are considering that the markets that don't have, there is no arbitrage in the markets, these two, they should be the same. And again here, just considering that the portfolio we have here can be writing, the portfolio can be writing at the value of the option minus delta, but in this case delta is the partial derivative of v with respect to s times s. So we're making that substitution and making the quality of these ones, we are reaching to this equation that we need to calculate in order, we need to solve in order to calculate the value of the option. This is the Black-Scholes equation. And as you can see, it has interesting things. For example, as you can see here, the Black-Scholes equation, there is no information on the mu. There is no effect of the mu. So the mu, which is the average rate of growth associated to the asset, this has no effect here on this equation here. This is one thing. Another thing, we don't have any other information here associated with what kind of option we are considering here on V. What kind of option? There is no information. So in principle, all the options are following the same equation. So where is the information on the option? Information on the option, on different options, will be included in the boundary conditions, initial conditions that we need to include in order to solve the equation. Because this is the partial derivative equation here. Of course, I didn't say, but this is linear equation. This is second order partial derivative equation. If we analyze the values of the A, B, and C parameters that we define for the partial derivative equations, it will say parabolic equation. So, and the kind of option we are evaluating will be included in the kind of initial and boundary conditions that besides these equations we need to include in order to completely solve the Black-Scholes equations. So basically here we just made a very brief introduction and derivation of the Black-Scholes equation that we'll need to numerically solve.